Okay, so we're diving deep into a really fascinating paper today. It's called From Masks to Worlds, a Hitchhiker's Guide to World Models.
That's right. And it's not just another survey. It really lays out a specific, opinionated path forward for AI. It charts this history, from the masked models we started with.
Like BERT and MAE.
Exactly. All the way to what they call these future self-sustaining worlds, true world simulators.
And their core idea, the main definition they're pushing, is that a true world model needs three specific things working together.
Yeah, three essential subsystems. There's the generative heart, they call it G. Then the interactive loop, which is F and C.
F for the filter, C for control.
Right. And finally, the memory system, M. Get those three synthesized, and that's a world model, according to this guide.
And they map out this evolution across 5 stages. Stage I is those foundational mask-based models.
Learning representations. Stage 2 builds on that. Unified models. Single architecture, handling different kinds of data, different modalities.
Then stage 3, this seems like a big step. Interactive generative models.
Yeah.
Closing that loop between action and perception.
It is a huge step because interaction needs stability over time, which brings us to stage 4. Memory and consistency. You need mechanisms to keep things coherent.
And all that culminates in stage V true world models, where you get persistence, agency, and emergence happening naturally.
Exactly. And the key insight, the thing they really hammer home, is that today's big models, even the huge multimodal ones like Gemini or GPT-4o, they're stage 2.
Impressive, but still stage 2.
Right. They might be precursors, but they don't have the dedicated architecture for real-time interaction, that's stage 3, or the robust memory for stage 4. You need those to actually get to stage V.
Okay, let's unpack that blueprint a bit more, because they're careful to define what they mean by world model, right? It's a specific path.
Very specific. They call it the narrow road. They're not really talking about, say, the simulators used purely for RL control, like Dreamer, or those LLM agent societies like generative agents.
Those are related, but different branches.
Yeah, this paper is focused squarely on systems built with this specific GFCM architecture in mind.
So let's look at that required anatomy. Why are current models, even the big ones, not quite there? It starts with the generative heart.
G.
Right, G is the foundation. Think of it as the basic physics engine. It's formally described by that probability distribution.
So G handles predicting what happens next. The dynamics, 0 lets T plus $1 and a given action act dollar. It generates what the agent sees, the observation hot dollar.
And maybe even predicts things like rewards or if the task ends. It's all about generation, pure passive simulation.
But a passive generator isn't really a world you can live in, is it?
Exactly. That's where the interactive loop, FC, comes in. This is the crucial part for making it more than just a sequence predictor. It's about enabling an agent to act within the generated world.
So F is the inference filter. That's how the model takes in a new observation, hot dollars, and figures out what it means in the context of its history, updating its understanding of the state 0 honor, updating its understanding of the state 0. Yeah, it's the real-time interpretation piece, what just happened. And then C is control. That's the agent's brain, basically.
Right.
The policy scale for choosing actions and the value function V omega for planning or judging states.
Having dedicated F and C subsystems is what enables true interaction and real-time adaptation.
Precisely. And then to make the world stick together over time, you need the memory system, M. This ensures the past matters, that actions have lasting consequences.
Formally, that's the memory update function, AT1, ZT1, using some kind of recurrent state AT1.
And this breakdown, GFCM, really clarifies the paper's argument. A big stage 2 model, say GPT-4o, has an amazing G. It can generate incredible stuff.
Absolutely.
But it typically lacks dedicated F and C components designed for an agent living inside it. And its memory M is often just the context window, right? It's not usually a persistent structured state. That's why they argue these models fail the persistence test needed for stage V.
Okay, that makes sense. So let's trace the path. Stage I, mask-based models. This feels like the bedrock modern AI is built on.
It really is. The whole mask, infill, generalized paradigm, it just took over.
Starting with language, right? BERT was a breakthrough with its bidirectional context.
Yeah, seeing the whole sentence. Then Roberta improved things with dynamic masking. And that lineage leads, eventually towards iterative refinement, diffusion models for generation.
And the amazing thing was how universal this masking idea turned out to be. It jumped straight to vision.
Right, like MAE. Masking out, 75% of image patches? Forcing the model to learn really deep visual features, that became a powerful G component for vision models.
And for actually generating images, you had masked GIT, Misonic,
Mm-hmm.
using that same masked infilling idea but for synthesis, often in parallel.
And it didn't stop there. Audio got Wave 2 Vec 2.0 using masked prediction on latent speak representations. 3D point clouds got point BERT. It's just a fundamental technique.
Which sets us up perfectly for stage 2. Unified models, this is where we are now, largely. Big industry models.
Exactly. The idea is one single architecture, often a transformer backbone, that can process and generate across different modalities, text, images, audio, maybe video, using a shared approach.
And the paper highlights 2 main tracks to get here.
Kind of, yeah. One track started with language models, autoregressive ones, and extended them. Think Chameleon, the EMU family. They made LLMs truly multimodal, often mapping everything into a shared token space.
And the other track.
That one uses more of a mask-based diffusion approach. Systems like MMATA or Illumina Doom fit in here, or generalizing visual techniques like taking latent diffusion, unidiffuser, or masked image modeling, MUDIT, and making them work across modalities.
The result being these incredibly powerful systems like Gemini, GPT-4o.
Absolutely. Industrial scale, amazing capabilities. But, and this is the paper's core critique of stage 2, they're mostly doing single-shot generation, or maybe step-by-step editing.
You give it a prompt, it gives you an output, maybe you refine it.
Right. They don't have the built-in machinery, the dedicated F&C, for continuous, real-time, closed-loop interaction with an agent inside the generated content. That's the whole point of stage 3.
So stage 2 models are like incredibly sophisticated image renderers or text generators, but they don't create a place you can act in continuously. Stage 3, interactive generative models, is about building that place.
Precisely. The shift is huge. The model isn't just generating based on a starting prompt, it's generating continuously based on a stream of inputs or user actions in real time. Low latency becomes critical.
We can see this clearly in language, right?
Right.
Moving from older text adventures.
Yeah, things like Text World, which had fixed environments, parsers,
Yeah.
very structured.
To something like AI Dungeon, where the large language model is the world. It generates the story, the consequences, everything based on whatever you type.
Exactly. It's co-authoring the narrative with you, dynamically. An unbounded world generated on the fly. The model becomes the dungeon master, the world itself.
And we see a similar evolution in video and spatial domains.
Definitely. Early work used latent space models for planning NRL, like Dreamer. Then we got things like GameGAN, trying to be neural game engines. Control got more sophisticated too, moving towards natural language commands like in PGM.
But the paper really highlights the Genie series as a key indicator here.
It does. Genie 1 was basic, 2D worlds, very limited memory, like 16 frames.
Okay.
Genie 2 scaled up, bigger, sort of quasi-3D environments, better object permanence. It remembered things for longer.
And then Genie 3. That was the big one recently.
That's the one that really turned heads. Real-time interaction, 720p, 24 frames per second, generating a controllable world from text prompts and keeping it coherent for minutes. That's a major leap.
Combine that with other approaches like World Labs generating explorable 3D scenes.
Yeah.
It shows real-time interactive worlds are becoming feasible.
It does. But this is exactly where the challenge highlighted by the paper comes in, the consistency problem.
Right, the trade-off. You've got models like Genie, these implicit frame-by-frame generators. They're super flexible, but they can easily hallucinate or just drift. The story goes off the rails, objects pop in and out.
Yeah, that's the drift issue. On the other hand, you have explicit 3D scene generators, maybe based on nerfs or meshes like World Labs. They have strong geometric consistency. Things tend to stay put.
But they might be less flexible, harder to modify dynamically.
Potentially, yeah. So this lack of reliable long-horizon coherence, this drift problem, is precisely why we need stage 4. You can interact for minutes now, but what about hours, days?
Stage 4, memory and consistency, making the world stable and durable over much longer timescales.
Exactly. How do you give these models a robust, coherent state that persists? There are a few main strategies being explored.
First one seems obvious if you know LLMs. Retrieval, externalized memory.
Right. If the model's internal context isn't enough, just let it look things up. But it's evolving beyond simple retrieval. Think retro, using huge external databases.
Or MemGPT, which is a really interesting idea. Treating the LLM like an operating system managing its own virtual memory.
Yeah, explicitly deciding what context is important, what to keep, what to page out. It's trying to engineer a better M system externally.
Okay, so that's external memory. What about building it into the model itself? Architectural persistence.
This is where you see some big architectural debates. The paper sort of groups them into reformists and revolutionaries.
Okay.
The reformists try to extend the standard transformer attention mechanism, make the window bigger using recurrence like Transformer XL or the compressive transformer, or use compression tricks like Perceiver AR or the recent Infini attention, stretching the context.
And the revolutionaries.
They say the quadratic cost of attention is the fundamental problem. We need to ditch it. This is where state space models like Mamba come in, or RetNet. They use linear time recurrent updates. Theoretically, they could handle near infinite context.
And then there are just massive engineering efforts.
Right, like LongNet or ring attention. Using distributed compute to handle enormous context windows pragmatically.
But just having a huge memory capacity isn't enough, right? You still have the drift problem we saw in stage 3. So stage 4 also needs ways to regulate consistency.
Crucial point. Especially for those implicit video models. How do you stop small errors from accumulating and making the simulation bizarre over time, while also not just forgetting everything that happened earlier?
It's a balancing act.
Exactly. So you see techniques like FramePack using occasional high-quality keyframes to kind of anchor the history, reset the drift, or MOSI, which uses sparse attention to focus only on relevant chunks of the past.
And for the explicit 3D models, geometry helps, but...
Geometry gives you spatial consistency, but you still need to track changes. How does the world update when an agent moves something? Systems like VMem try to solve this using circle-based memory tied to the 3D view. It's like a dynamic map that gets updated.
So stage 4 is really about building stateful computation, making the history matter, and stay coherent.
Yes. And it leads to this really interesting question the authors raise. Is persistence something that will just emerge if we scale context windows infinitely using architectures like Mamba? Or do we absolutely need explicit, carefully designed memory management and consistency mechanisms like VMem?
Brute force scaling versus disciplined memory engineering.
That's a good way to put it. Which path gets us to true long-term coherence first? It's a huge open question.
Which brings us, finally, to stage V. True world models. The synthesis, G, F, and M, all working together seamlessly.
And the key idea here is that the defining properties of these worlds aren't explicitly programmed in. They emerge from the system's operation.
What are those defining emergent properties?
They list 3. First, persistence. The world state has real consequences that accumulate over time, totally independent of whether a user is logged in or not. It has its own history, its own momentum. That's the M system fully realized.
Second, agency. The world isn't empty. It's inhabited by multiple agents, humans or AIs, pursuing their own goals. This really puts the F&C components to the test, managing a whole society, not just one actor.
And the third, the most profound, is emergence. This is where you see unexpected macro-level phenomena, maybe social structures, economic patterns, complex group behaviors, arising purely from the low-level interactions of the agents within the world's rules, the G component.
Getting to this synthesis, this stage V, presents some massive challenges, though. The paper calls them the 3 frontier challenges.
Yeah, first is the coherence problem. If the world is generating itself, how do we even know if it's correct or true? There's no external ground truth anymore. We need ways to measure its internal, logical, and causal consistency. Is it making sense on its own terms?
Yeah, it sounds hard.
It is. Second is the compression problem. The history of a persistent world is potentially infinite. How does the model represent this efficiently? It needs to learn the right abstractions, the causally sufficient state, just enough information to predict the future reliably without storing every single past detail.
Because storing everything is computationally impossible.
Exactly. And complex systems are often computationally irreducible. You can't perfectly predict their future without simulating them step by step. So effective state compression is vital.
And the third challenge sounds particularly tricky. The alignment problem. Squared.
Right. It's not just aligning a single AI anymore. First, you have to align the underlying laws of the world model itself, the G component, the physics, the substrate. Make sure that behaves as intended.
Okay, baseline alignment.
But then you also have to worry about the alignment of the emergent dynamics of the multi-agent society living within that world. What happens when these agents start interacting in unpredictable ways? How do you ensure that aligns with human values? It's alignment on top of alignment.
Wow. Okay. So the paper's conclusion is pretty profound then. Reaching stage V isn't just about better simulators.
No, it's transformative. They argue that a true Stage V world model becomes more than a simulator. It becomes a scientific instrument, a computational crucible.
A place to run experiments.
Exactly. Controlled experiments on complex adaptive systems, economies, cultures, social dynamics, things that are impossible or unethical to experiment on in the real world. It could be a completely new way to do science.
That's a powerful vision. So thinking about that stage 5e bottleneck, again, the infinite context architectures like Mamba versus the explicit memory discipline like VM, where do you think the research needs to focus to unlock stage V first? Is it about scaling the architecture relentlessly or getting really smart about managing state and consistency?
That's the million-dollar question, isn't it? Maybe it's a bit of both, but the
Yeah.
path we take there, yeah, that's going to define the next few years of AI research in this area. It's a really exciting time.